started. So I believe this is our penultimate seminar of the semester. So I'm very happy to introduce Professor Maria Brunetti to you. Our speaker completed her undergraduate studies at University of Naples and earned a PhD from the University of Birmingham, where she was working on rare kaon decays with the Na62, is that how I say that? Na62 experiment at CERN. And then after that, Maria moved into neutrino physics during a postdoc at University of Warwick, contributing to event reconstruction for Dune and Microboon, where they served as reconstruction group convener from 2023 to 2024. Maria is now at KU. You joined a year ago? About a year ago, yep. Maria's working on Dune and SBND, which is the short baseline neutrino experiment at Fermilab. Maria's remaining active in Microboon and currently co-leading the development of Pandora for the Dune near detector. Today, Professor Brunetti is going to tell us about unlocking discovery at liquid argon neutrino experiments with Pandora event reconstruction. So we are very thrilled to have you. So let's give her a round of applause.
Thank you. I just hold this.
Just hold it if you want to.
Yeah. I think it's fine. Yeah. Okay. Yeah. Thank you very much, Matt, for the introduction, and thank you very much for the invitation. And yeah, I'm very happy to visit Wichita State University and my colleagues here working on Dune and meeting many new colleagues. And this is also an occasion for me to visit a bit more of Kansas. I've not really ventured much further out than Lawrence so far, so excited to visit Wichita. So thank you very much. And yeah, so as Matt said, I'm going to tell you about liquid argon neutrino experiments, why they are exciting, what we're trying to do with these experiments, and then what is my, let's say, biggest scientific passion at the moment is to work on event reconstruction, as this is really a step that is between the detector information and the physics analysis. So it has a really crucial role, and I'll tell you more about it, hopefully convince you that is really cool, important, challenging, but important by the end of the talk. So I just have a brief outline here. So I will address the following questions today. Why are we interested in studying neutrinos? Why is the international particle physics community really investing in these experiments over the next decades? What kind of experiments will we use to study neutrinos? And then I will focus in particular on the liquid argon time projection chamber technology, which is the technology of choice for US-based experiment for oscillation of neutrinos. And I will give a very brief overview of the current LRTPC designs, because we say we're using LRTPCs, but when we say this, we're not really saying we're using one type of detector. Really, there are so many differences between all the different LRTPCs we are building and testing and prototyping that it's worth focusing on that for a moment. And then I'll talk about event reconstruction. I will talk about how all these different landscape of different LRTPC designs creates new challenges at the event reconstruction level, because we want to be able to be flexible enough to accommodate all these different designs, and why this is an important step in unlocking the physics potential of these experiments. And this here is just ChatGPT's idea of a recipe to turn LRTPC inputs into something, and there's a LRTPC cake there for you. Okay, so this is a scheme you're probably most of you familiar with. This is the particle content of the standard model, our best description of particle physics. Obviously, this may not be complete. We know that we don't understand what dark matter is, so we might have to extend this. There may be new particles out there that we are not aware of. So again, we may need to extend this. And while many of the particles on here, we've been aware of them for quite a long time, and we've studied them over the past many decades, I want to focus today in particular on the bottom right corner here, which is the neutrino sector. And I must say neutrinos are not a new idea, right? They've also been around for quite a while. They were proposed in 1930, discovered in 1956. Then we discovered this peculiar behavior they have. There is the neutrino oscillation, which I will tell you a little bit more about soon. But they are still of high experimental interest. So we're going to talk a little bit about that. First, I want to introduce the concept of neutrino oscillations. Again, for if there's anyone who's not familiar in the audience today. So neutrinos are producing what we call flavor states. So states with defined flavor. This means that when they get produced, they are producing association to a charged electron of a specific type. So this could be electron flavor, muon flavor, or tau flavor. We know this because then this neutrino doesn't go ahead and interact and produce a different type of charged electron. So we know that it's a specific feature of this neutrino, what we call flavor. However, we then discovered that these flavor states are not the physical neutrino states. And in fact, there's this quantum mechanical phenomenon of mixing, according to which the flavor states of neutrinos are a linear combination of 3 different physical neutrino mass states. And these have different masses, so they propagate at different speeds. So if you start off with an electron flavor neutrino and you let it travel for a while, then the probability of observing a different flavor after a certain distance of travel will be different from 1. Okay, so you could observe a different flavor neutrino. So, and this is because these 3 different waves will be out of sync with each other. So here at the bottom, I've put another famous expression, which is the probability for appearance of a new type of neutrino in a simplified 2-flavor scenario. So here I just want to point out the parameters that come at play. So we have a couple of parameters I put in green, which are mixing angle, or the square sign of a mixing angle, and the difference between mass squared of the 2 neutrino mass states. And these are fundamental parameters of the theory. We don't change them. But what we can change when we design a neutrino oscillation experiment are the pink parameters there, the experimental parameters that are the baseline over which the neutrinos oscillate and travel, and the energy, obviously. This is true when we are designing an accelerator-based neutrino experiment, for example. If we're just getting neutrinos from the sun, we don't really change the baseline, we don't really change the energies for these neutrinos. But as you will see, the experiments I'm going to talk about will be experiments that we made really conscious choice as to what baseline we want to use and what energies we want to use. And very quickly, going over this slide, this quantum mechanical mixing, if you consider all the 3 neutrino flavor and all the 3 neutrino mass states, is given by a 3x3 unitary matrix. And here I've put it, the composition of this matrix in 3 other matrices that have the parameters that are most relevant to oscillations to the mixing of 2 specified mass states. And then also different experiments are most sensitive to measuring different parameters, because again, in this formula I showed you here, the L over E, you want to be able to observe the oscillation, so you need the L over E to be comparable with the inverse of the delta M square in order to be able to observe an oscillation. So, and the other thing I want to point out here is that the parameterization here is in terms of 3 mixing angles and 1 phase delta. It's a complex phase, and this phase is related to a possible delta CP, possible CP violation in the neutrino sector, which means that if CP is violated, with our experiments that study both neutrinos and antineutrinos, we would observe different kind of behaviors. Okay, so there are many physics opportunities with neutrinos. Some of them are related to us wanting to understand neutrinos for neutrinos' sake. So we want to measure all these parameters I was telling you about the mixing and the square mass differences. And also, we don't know, because oscillation experiments are sensitive to the square mass differences, we don't know the absolute masses of neutrinos through these experiments, but we know the delta of the mass squared. And there are two possible scenarios based on this. So if mass of state 2 is larger than the mass of state 1, then for 3, there are two possibilities. Even it's at the top or it's at the bottom. So this is what we call the normal or inverted mass ordering. And then there are other questions, such as, are they the same as their antiparticle? But these are not questions I will focus on today. Also, neutrinos are windows onto new physics because if there are additional neutrino types, they will oscillate with the 3 neutrino types we know of. And so we could learn of the existence of these additional neutrinos. And we can also use them as probe for astrophysical processes. So there's a lot of people interested in the space, I think, here. So neutrinos are they are the first particles that arrive to Earth from, for example, from supernova bursts. And we will see them in our neutrino experiments. And also we can study solar neutrinos, neutrinos from the atmosphere, etc. And you can see here, and this is a very famous also plot, you can see the very broad energy spectrum for the neutrinos. So based on the source of the neutrinos, they will have a different energy range. And as you can see, we go from the very small to the very high energies. Okay, so there are a lot of cool facts about neutrinos. Another cool fact is that they are very abundant. They are the second most abundant particle in the universe after light particles. But then how come, if they're so interesting and there's so many of them, that we've not studied them before, and it's been so long since we discovered them that we're only building these experiments now? And one of the reasons is that they only interact weakly. And so we really need high stats. We need to make a lot of neutrinos in order to be able to study them. Obviously, another reason is that in order to see the oscillation behavior, we needed to study neutrinos at the correct distances, so that wasn't immediately picked up in the very first experiments that studied neutrinos. So experimental neutrino sources here are neutrinos from space and the atmosphere, or accelerator neutrinos, or neutrinos produced in nuclear reactors. And I will focus on the first two categories here. Okay, there are a couple of technologies of choice for the future for studying neutrino oscillations over the next few decades, and they are the liquid argon time projection chamber on the left and the water Cherenkov technology on the right. These are not new technologies. They have been around a while. So Hyper-K, it's a Japanese experiment that's chosen water Cherenkov as its technology for future experiment. And this is, in fact, the same technology as Super-K, but with a bigger detector. So it's not new, but RTPCs also are not new. We have several RTPCs that have already taken data, are taking data right now. But this is the technology that the future deep underground neutrino experiment has also chosen. And this is an experiment under construction that I will tell you more about in the rest of the talk. So I'll focus on the RTPC technology. So I want to tell you a couple of words about DUNE, and then a couple of words about a different neutrino oscillation program, which is a short baseline neutrino program at Fermilab. So let's start from DUNE. DUNE is a long baseline oscillation experiment. It's still under construction for a few years still. And so it will use a beam that is made of Fermilab. That will be the most powerful neutrino and antineutrino beam in the world. And a peculiarity of this beam is that it will use a wide energy spectrum, a wide band energy spectrum. And I will tell you why this is important in a little bit. And also a long baseline. This is also important. And yeah, so effectively, this allows us to observe two oscillation maxima. It gives us a lot of spectral information that we can use to make a lot of neutrino fundamental parameters measurements all in one single experiment. This is an experimental first. So we make the beam at Fermilab. We let the neutrinos travel underground. We have a near detector complex, which is also a Fermilab that both KU and Wichita are involved in. And then also we have 4 large-scale liquid argon time projection chamber modules all the way in South Dakota at SURF at the far side. And so Dune will proceed in two phases. There will be a first phase with a lower intensity beam and then just two of the far detector modules and an initial near detector configuration. Okay, I guess that's it. And then we'll upgrade the beam and have more far detector modules. The technology for the last two modules is still being prototyped and discussed. It's still open. And there may be upgrades to the near detector too. So the Dune program is very broad. So we want to make all these precision measurements of fundamental neutrino parameters. So we will measure the neutrino mass ordering in about 3 years since the start of accelerator data taking. And we will also test the 3-flavor unitary mixing model and make precision, and as part of this also make precision measurements of fundamental parameters such as the CP violating phase delta, find the octant of θ23, etc. We also will study astrophysical neutrinos, as I was saying, and study BSM physics processes. Okay, and here just one slide. I don't want to go into a lot of detail about this, but just to show you why the approach that Dune is taking is powerful. So you can see on the top right corner, the flux at the near detector, and you can see that this spans a couple of oscillation maxima. And so the flux is pretty high for both oscillation maxima and the minimum in between. And also you can see a long tail at high energies. We even have significant flux above the tau neutrino, say the tau production threshold around those 3.5 GeV. So we can really do 3-flavor oscillation measurements. And here on the bottom, you can see these plots that are showing the number of electron neutrinos and electron antineutrinos on the two axes in 3 different energy bins. And the ellipses here represent the normal and inverted ordering. So you can see that the ellipses are separated in all 3 energy bins, and the separation changes a bit depending on the energy bin you're considering. And so you can see that Dune will be able to tell apart the mass ordering. This is thanks to the long baseline, thanks to the fact that matter effect will change oscillation probabilities different from for neutrinos and antineutrinos. And you can also see that walking across the ellipse, you walk across different values of the CP violating phase. So you can see that in some of the energy bins, these ellipses are flatter, but in some others, they are not flat. So we will be able to resolve this degeneracy that could exist between, under some scenarios, between mass ordering and delta CP. Okay. A couple of words on the short baseline neutrino program as well. This is cool for many reasons. One of them is it's currently taking data. So we have this really nice LARTPC data coming from this program. So this is a short baseline program. This means that the near and far detector are just a few hundred meters apart. It's a Fermilab on the booster neutrino beam line. It's the same beam line where microBoon took data, if you're familiar to the microBoon experiment, and also where the mini-Boon experiment before that took data as well. And mini-Boon is one of those experiments that observed some anomalies. So in a sense, this SDM program is there to fully study neutrino oscillation on the same beam line as mini-Boon in order to study this anomaly, among other things that this program will do. So yeah, just a word on this reported anomaly. So mini-Boon was a mineral, was a sphere full of mineral oil. So it was using Cherenkov scintillation as detection mechanisms. And one of the limitations of mini-Boon was the limited ability to resolve, to separate electron and photon signatures. They both look like fuzzy rings, as you can see in this top right event display. And so when they reported this excess of activity at low energy in the electron neutrino energy spectrum, there was a question there. Is this just us mismodeling this electromagnetic activity? Or is this new physics? Or is this compatible with oscillations between the 3 active neutrino types and the light sterile neutrino? So I will show you why SBN has a much better technology to study this question. Obviously, Microboon also has been studying this previously, also using the RTPC technology. But I just also want to mention the program is much broader than this. SBN will also more generally search for oscillation between active and sterile neutrinos, not necessarily reproducing this anomaly, and search for new physics processes and perform a broad program of cross-section measurements. Now, we care about cross-section measurements because they also feed into our future experiments like Dune. Okay, so why is this LAR-TPC technology so good? So this is a sketch of a LAR-TPC drift volume. So I'll just talk you through what's happening here. So imagine having this neutrino represented by this dashed incoming line, and it interacts with the argon in this box in this sketch. And it will produce charged particles that will travel in the detector, will ionize the liquid argon, and then these electrons that have been stripped off, the argon atoms, they will be free to drift. There's an electric field, so they will be drifted towards a series of readout planes. Now, caveat, this is one type of RTPC. I did say we have many types of RTPCs, and this is a type of RTPC that uses 2D readout. So these planes of wires, in particular, wires that have different orientations depending on the plane that they are part of. This is like taking pictures from different angles. Effectively, the idea is that we will obtain 3 different projections of the same interaction, and this will be our handle to then reconstruct the interaction in three dimensions. Now, we also have emission of scintillation light. We know the big advantage of scintillation light is that it's fast, and so we can use this as timing information as well. Though some RTPCs also can provide some positional information using scintillation light. I will just very briefly mention this later. And this is the famous Fermilab produced, I think, a video of a RTPC. So you can see the neutrinos coming in. One of them will interact, produce a couple of charged particles, a muon and a proton. So the yellow dots are the ionization electrons that drift towards this plane. And here you can see like a sort of grid. So this is an example, if you like, of a 2 readout plane LRTPC with perpendicular wires. But in reality, we typically use 3 planes to have redundancy there. Okay. Okay, and these are the first images I think I'm showing you of LRTPC event displays. You can see these are beautifully high resolution images that we get from these detectors. And how to read these images. So on the x-axis here, you have a coordinate that is derived from the wire that was hit in that readout plane. On the y-axis, we have a coordinate that is derived from the drift time of the electrons. And then the color code is the charge that was deposited. Okay, so we really combine tracking and calorimetry in this detector. And you can really see the superb resolution of these images of the order of millimeters. And something I want to talk about is why these are so much better suited at overcoming the limitations of experiments like Mini-Boon. And you can see that here we have a couple of event displays. On the left-hand side, you can see in this event a couple of electromagnetic cascades, this gamma 1 and gamma 2, coming out of likely the decay over pi 0. And so we can exploit the fact that photons have this conversion gap. So they are neutral particles, so they don't start depositing charge right away. They first need to make an electron-positron pair. Once they've made that, you start seeing the shower. So you see this conversion gap here. And electrons, on the other hand, they're charged, so they start depositing charge right away. So this is one handle we have. The second handle is the energy deposited at the start of the electromagnetic shower. That for photons is twice as much as the energy deposited by the electron. Why is that? Because we said photons produce a pair. So at the start of the shower, there will be 2 electrons, not just 1. So as you can see here, we can get some nice separation from LAR TPCs. Okay. As I've moved now past the introduction to our experiments, I want to talk a little bit about what these different designs that are out there are for RTPCs. So we have different types of charge readout. I've already mentioned, I've shown you some examples of RTPCs that used wire or strip-based readout planes that give us images, effectively, 2D representations of the neutrino interaction. But we do have some detectors, in particular, this is the technology for the Dune near detector, that use a native 3D pixel readout. This means that we have one extra coordinate right away. So we have, I think I've got a sketch in a little bit that will make it obvious what I mean there. But effectively, we have native 3D information, which is obviously better. Some other things that can change are the type of optical readout, the photodetector coverage, but also things like what is the drift length, what is the drift direction. So there's really a lot of different options there. And I want to very quickly mention, so for the first two modules of the Dune far detector, we have a couple of technologies that we have chosen. One is the horizontal drift far detector. As the name says, the drift is horizontal, and it's about 3 meters long. And it's got a wire-based readout. And yeah, I guess people like giraffes and tennis courts. So I've moved to this new system of units now. For the vertical drift far detector, in this case, the drift is vertical, again, as the name says. The drift is also longer, and the readout is based on printed circuit boards, but it's still 2D, okay? And then, as I said, for module 3 and 4, the technology isn't quite fixed. I am hoping that at least one of the far detector modules will be pixel-based, like the near detector, so that we have the same technology across near and far detector, and that would be really nice, and probably also really useful in controlling systematics there. So, but let's see. I don't know what's going to happen. And okay, a few words on the near detector then. So first, I want to mention why the near detector is important. So the oscillated neutrino spectrum at the far detector depends on all of these ingredients here. So flux, cross-section, detector response, and the oscillation probability. And we can constrain our uncertainties on flux, cross-section, and detector response with the near detector, and also characterize, really study the oscillated neutrino beam. So we have this triplet of detectors, NDLR, the mu spectrometer, and SAND that are going to perform this task. So one of them will be liquid argon-based and pixel readout. This is NDLR. This is to match as much as possible the technology for the far detector. Then there's a mu spectrometer. Why do we need this? Because the near detector is small. We cannot make it very big. And so it will not contain the muons that come from interactions of neutrinos in NDLR. So we want a separate system to study those and study the charge and the momentum. And the cool thing is that NDLR and TMS, they also move off axis. So they sample the beam, the beam flux at different angles of axis. And the beam flux changes because of the different pion decay kinematics. And we can use all these different fluxes that we measure to create a prediction for the far detector oscillated spectrum with smaller experimental uncertainties. The third detector here is SAND. It's a beam monitor. This will not move off axis, but it will sit in the beam line and it will just characterize the beam. So this was it for the motivations. Here I just wanted to show you currently what one of the near detector, liquid argon near detector modules look like. This is a prototype argon cube 2x2 detector. Again, as I was mentioning, this will have native 3D charge and light readout, and also the optical system is confined here to each module, so light doesn't go through the other modules, and this helps with the light pile up effectively. And this is a small but complete version of NDLR. And so we will have our argon cube 2x2 detector has 4 of these modules, so that's why 2x2. And they're also using a couple of different light detection systems. I also want to say a couple of words on the SBND detector. Okay, this is cool in a different way. So this is still like a more traditional RTPC. This uses wire readout. However, what is quite novel is the light detection system, because to maximize the number of detected photons, the TPC cathode, which you can see here in the middle between these two drift regions, is covered with reflective foils. So you can see here at the two end faces, the purple ones, this is where the photodetectors are. There's two different types of photodetectors here. And so they will receive both direct light that is emitted say, by particles as they travel through, but also a reflected component that has arrived to the cathode first, and then it's been reflected back. So this is one cool thing, but another cool thing is that for all these elements, for the photodetectors, you need to wavelength shift them in order you have to wavelength shift the light in order to be able to detect it with these sensors. So the cathode is coated with this wavelength shifting material, but only some of the photodetectors are. This means that you can then tell which component of light was direct and which component of light was reflected by studying the ratio of how much light you get on these different photosensors, the coated ones and the uncoated ones. Obviously, the direct light, if it hits an uncoated photodetector, it will not produce a signal. So this is a very cool thing. And this feature gives us the ability to get information on the mean drift distance as well. So positional information in addition to time information. Okay, now I've spoken a lot about different RTPC technologies, but there's not just different RTPC technologies, there's also different environments we can place our detectors in, different things that we want to study. And these choices all have an impact on the physics, and they require tailored approaches to extract the information that we actually care about. So just to give you an idea here, on the left-hand side, this is an event display from a Proto-Dune single-phase run where there was a large cosmic shower. So you can see all these cosmic rays crossing through, making it harder to find the test beam particle in this event. In the middle, you can see what the pileup will look like at the Dune near detector. So that's a lot of pileup, several tens of neutrino interactions and muons coming from interactions that happen in the rock prior to the neutrino arriving to the liquid argon. So it's going to be a real mess. And on the right-hand side corner, a different type of challenge. So that's a supernova neutrino simulated event. So here you can see the signal election here. I don't know if it says here, okay, for a 15 MeV supernova neutrino signal, you can see that the signal is a tiny blip. And there's all this radiological background that looks very similar to the signal. So this is a different type of challenge, trying to then recognize which one is the electron, is the neutrino, so the electron from the neutrino, and what is just background. So lots of different challenges. Okay, I'll go very quickly on this one. I want to get to pattern recognition and tell you a bit more about how we do it. So this slide is just to say, when we go from raw inputs to physics quantities, there are several steps that are involved. The first steps are just signal processing, deconvolution to deconvolve signals from adjacent wires. And again, this is more of a 2D paradigm that I'm talking about here. And then there's a hit finding step. So we have these waveforms on each of the wires, and finding peaks in these waveforms, we can identify we can produce what we call a hit. So a charge deposition on a given wire at a given time. So these are our inputs to pattern recognition. So here's a simulated event, so a charge current quasi-elastic scattering event. And you cannot see the neutrino here, but you can see the vertex between the proton and the muon. This is where the neutrino interacted. These are two charged particles that are produced in this interaction. The muon goes some way, it decays, and it makes an electron and a pair of neutrinos. So what does this event look like in a wire-based TPC, LRTPC? Like what I put here on the right-hand side. Okay, so top, center, and bottom are the three different projections we get from different readout planes. And you can see that these three images have a similarity. Obviously, the similarity is given by the time coordinate. The time coordinate is in common because obviously when the electrons arrive on the wire planes are very close together. So these, say, meaningful events will be aligned in time. So the point where the neutrino interacted is at the same drift coordinate in all three images. The point where the muon decays is at the same drift coordinate in all three images. So this is a handle that can be exploited in pattern recognition. Now, you may think, okay, this is a simple job. I could tell you very easily what's going on here. But things do get more complicated when you go up higher up in energy. So here are a couple of deep inelastic scattering events, and you can see that we start to get multiple tracks and showers being produced in these events. And I got another. This is an even higher energy, a couple of interactions, and you can see that it starts to become tricky, possibly even for a human, to tell apart different particles. Okay, these events start to become messier, and this is why pattern recognition is a tricky, it can be a challenging task. So how do we do this? Having a single clustering reconstruction approach is unlikely to work for all this broad range of topologies and scenarios that I've described. So the approach I use I work on is Pandora's approach. Pandora is an event reconstruction software. It's a multi-algorithm reconstruction software. This means that it breaks down the problem in individual logical steps and tackles them one by one. And this is also where its power lies in adapting it to new detector technologies, because you can kind of pick and choose what algorithms you want to use. You can tailor specific algorithms for your specific use case. So for example, in the case of a 2D RTPC readout, you can see what the main steps are. So we first do the reconstruction in 2D, then we match 2D patterns across the different readout planes to construct 3D objects. And then we have other steps like vertex finding, building this hierarchy of particles, so attaching the particles onto each other in the most logical way, and tagging particles as tracks or showers. And very quickly, to not bore you too much with the technical details, but these, let's say the Pandora event reconstruction software uses three different components. One is this client application. This is the interface to the detector inputs. This is the bit you actually go and change when you want to interface to a new detector, maybe a completely new experiment. And you have to make sure that the inputs are being propagated correctly. But then the box at the top, the Pandora software development kit, this contains core functionality to create, access, and modify objects. And then and this is common to all RTPC experiments and the use cases. And then you have these algorithm libraries, and these are the ones that contain the pattern recognition logic. So the algorithms that actually go and do the reconstruction are here. And this kind of approach is very good because you know what component you have to change, and the rest you don't have to touch. Okay, so I have a few slides. I'll try to go quickly over them of some of the main steps in this multi-algorithm approach. For example, there's an initial clustering step where you merge together the hits that are contiguous and represent an uninterrupted contiguous set of hits. So you can see this on the left-hand side. And then there are some other algorithms that associate all these, if you like proto-clusters together to get complete objects, like in this case of this pair of crossing muons. And here are other examples of association algorithms. For example, algorithms that look particularly at topologies that have a longitudinal direction, or algorithms that are designed to cross detector gaps. Here is an example use of deep learning. I know people in the group work on vertex finding for other neutrino experiments. So in Pandora, we use a deep learning approach to vertex finding. And the idea, and we do this actually before the pattern recognition runs. So we analyze the input hits, and for each hit, there's a CNN that tells us, that assigns to that hit a distance class from the vertex, as you can see in the bottom left image. Then based on these distance classes, we can build a heat map, which is what you see in the middle. And then we still don't know where the vertex, the neutrino interaction vertex is. So you can then build these circular regions centered on the hits that have a radius that is the same as the predicted distance class from the vertex. And by intersecting all of these circles, we isolate the vertex location. And so we actually have a publication on this that you have put a reference to here. Again, going quickly on this slide, we also can build detector information into our algorithms. For example, here, I mentioned that we do the reconstruction first in isolation in each of the different readout planes, and then match it across these different readout planes. And we can exploit our knowledge of wire plane geometry. So for example, take a pair of clusters into planes and project them onto the third plane and see whether a cluster is found there where we expect it. If it is, then we do a kind of association between all the three clusters. And if not, we iterate and find another association there. I've shown you mostly track-like topologies. Shower reconstruction is quite similar. The main idea is trying to identify shower spines, so these main shower segments that we can then attach all other shower bits onto iteratively as branches. And we are exploring new approaches though. This is how development works. So we are also exploring new machine learning approaches to these kind of problems. And then I want to say a couple of words on the consolidated reconstruction. So the problem I've mentioned earlier is, for example, we may have a lot of cosmic rays at the same time as a neutrino or a test beam particle if the detector is on the surface, right? So we want our reconstruction to be able to reconstruct separately, to isolate the interaction from these other crossing cosmic rays. So this is part of a consolidated approach. And these are the main steps of this approach. We first reconstruct all input hits as cosmic muons. If the objects we reconstructed look like clear cosmic ray muons, for example, if they cross top to bottom, we take them, put them aside, and for whatever is left there, we just reprocess it with two different options, different algorithm chains. One that is cosmic neutrino, cosmic ray oriented, and one that is a neutrino oriented. So looking at finding a hierarchy of particle there. And then with these two outcomes, we pick the best one. And that's the outcome that then is persisted. Okay, so this is the first time I give a talk, like a seminar colloquium, since I started the new job working on the near detector. So previously, during my postdoc, I was focused mostly on the far detector. So it's the first time I talk a little bit about the work we are doing at KU and at Dune more broadly. So this is what I was talking about when I say that the near detector readout is different from the far detector. So on the left-hand side, the kind of wire-based readout I was mentioning before, and on the right-hand side, pixel-based readout. That is the approach being used at Dune and DLR. That said, future Dune far detector modules may also use this pixel readout. So what are the challenges at the near detector? So what I just showed you, the previous slide, is an opportunity. It's good to have this native 3D readout. But there are also challenges that come with reconstructing the near detector. And the main challenge is that the near detector will be located near the neutrino source, obviously, by definition. And it will see a lot of neutrino interactions in each beam spill. Okay, so we need new approaches, and we are studying new machine learning approaches to separate these muons, for example, that come from neutrino interactions that happen in the rock before NDLR, from the particles that are produced within the liquid argon volume. And there was a nice summer project a summer student was doing with us at KU on this. You can see what the core idea is on the left-hand side. Another thing that we have efforts on within the broader Pandora group is develop a new machine learning approach to slicing. So really separate different neutrino interactions from one another. And we are using, one of our collaborators is developing a graph neural net to do this job. So the power of Pandora is the following. We didn't have all these we still don't have all the components there in place for the best possible reconstruction of the view near detector. But the power of this multi-algorithm approach is the fact that we could take pretty much the reconstruction that we were using at the far detector and just change the interface to the near detector inputs, and then have a day zero reconstruction. So what was happening here is we were starting from the native 3D hits, projecting them onto planes. So this is not what we want in the longer term, but this is a day zero result, projecting them onto these readout planes, and then doing 2D reconstruction. So then doing the same thing with the far detector. Now, obviously, we started work to exploit more fully the input native 3D information that comes from NDLR. And we are developing all this new treatment for pile-up and cosmic and rock muon reconstruction. Also, something else that is powerful about Pandora and about the near detector is that we can move more towards a multi-detector reconstruction. Okay, so here, this is a very, very, very simplified sketch of NDLR and TMS. But as I was mentioning, TMS is there to catch the muons that come from NDLR. And so one possibility here is to do separate reconstructions for these two detectors and then try to match them across. But there is a lot of power to be a lot of potential to be explored in just doing a joint reconstruction where the NDLR bit can help doing a better TMS reconstruction and vice versa. So I would be very interested if, given the expertise here at Wichita State University, we could collaborate on this in the future as well. And another thing I want to mention is still in its very, very, very early days is to fold in optical information in the pattern recognition. Okay, so far there isn't any reconstruction approach that is really doing this. There are a lot of efforts and explorations going on the Pandora side and also on other sides. But this could also be advantageous, and we could use light information for a number of possible tasks. The primary one may be to help separate neutrino interactions from rock muon interactions, exploiting the timing information that comes from the light system, but there's a number of other possibilities. And this is novel, and really we are in the very, very early days. So I hope next time I give a talk here, maybe I'll be able to tell you something more about what we've done here. And also beyond the near detector, I mentioned the sophisticated SBND light detection system. And so that's also somewhere where folding light information in the reconstruction would be potentially really advantageous. So that's also something I'm interested in doing in future. The very last thing I want to do before closing off this talk today is to talk about reconstruction tailoring for analysis. And this really can help boost the sensitivity of our physics studies at these large TPC detectors. So what is the idea here? The idea is to tailor the reconstruction for each specific physics goal. Since we have this kind of a mix and match approach with the Pandora algorithms, we can have different algorithm chains, each of them being tailored for a different analysis use case. So we would, for example, identify what is the main performance metric that we care about. Is this the efficiency of a pi-zero reconstruction or the pi-zero mass resolution? Is this delta CP sensitivity? You name it. And the idea is that then we can go to the reconstruction. We can use what we call a cheating procedure to inject truth information at various steps of the pattern recognition and isolate the steps that would bring the most gain if we could improve on them, because we just plug the truth information there, so we do as good a job as we ever could. And then we do some bespoke development and optimization. Then we recompute the metrics we're interested in. Hopefully we have seen an improvement there. And then this can be an iterative procedure as well. And this is something that I'm really interested in being involved with, particularly with NDLR, prototype data analysis, and also at SBND. This is just, I don't know what's happened to the plot. I swear it was upright when I put it in my PowerPoint. I guess you all can turn your head around, you know. But this is an example of exactly this type of effort. This is the thesis of a PhD student that was in my group at work before I moved to KU, that I co-supervised, helped to supervise. And this was exactly aimed at improving the sensitivity for delta CP at Dune. And so One of the big limitations here comes from the possibility that electrons and photons are not correctly told apart. So for example, as I said, electrons start to ionize right away, but sometimes maybe the pathway that leads from the interaction vertex to the start of the electron shower has been wrongly assigned to another particle. Something has gone wrong. There were too few hits to make it into the object. And so this gets mistagged as a photon. And on the other hand, a photon shower that should have a gap, maybe it's wrongly claimed hits that belong to a different particles. Maybe because of the wire plane geometry, there was a sort of overlap. And so this can lead to confusion. And so Isabel here did some of these cheated studies where they isolated the steps in the pattern recognition that were like where this kind of issue was going wrong. Then they wrote new algorithms to improve it. And then they recalculated the delta CP sensitivity. And now if you turn your head, you can see that these curves go higher and higher in significance with more improvements that you make in the reconstruction. So yeah, sorry about the plot, but hopefully the gist of this was clear. And this leads me to the last slide. Obviously, there's something wrong with this one as well, but okay. So yeah, these are my conclusions. There are many open questions on the nature of neutrinos, many physics opportunities over the next decades. There's a lot we want to do, and we have amazing detectors to do it. And so this LARTPC technology is really, really crucial, but we need to be able to interpret these inputs we get from LARTPC in order to have the maximum sensitivity for our flagship goals. And I've told you a bit about how we do it. We're using Pandora. And yeah, I look forward to collaboration, especially with Wichita State University. Thank you very much.
Minutes for question.
Mm-hmm.
How long is that?
So I think millisecond long. I think over a few milliseconds we would get this drift. You know, the drift distance would take pretty much that long. Yeah. Yes.
That how long do you use any of the spill information to tease out different sets of spills?
Oh, like the structure of the beam spill, you mean? Within a spill, like just
yeah, like the tiny.
Yeah.
If it's multiple, if it's milliseconds, wouldn't it be multiple?
Yeah, so that's an interesting one. I think something Microbone did was analyzing the substructure of the beam spill. I don't know if we have, yeah, I don't know. I also obviously open the question to other Dune collaborators, but I don't know if we've done this sort of studies at Dune. So no, yeah. But yeah, interesting to look at. Yeah.
So same idea, the supernova spill, you say showing there were just little tiny blips because they don't go very far. In our research, we're looking at excited states that get produced in a similar, different neutrino interaction. Is it possible that in the argon you would get an excited state of the potassium nucleus that could for specific gamma ray energies with a certain energy, certain distance around it?
I think that's possible, but we're still talking about very low energies, right? Yeah, I think that's the main challenge there. But yeah, we have people looking into this kind of problem specifically. Yeah, I don't know exactly how well we will do. I mean, obviously, when you go a little bit higher up in energy, 20, 30 MeV, it starts to get a bit better, but for it's very low, few MeV signatures. It's a challenging problem. But yeah, definitely looking at this, the excitation photons and the like is definitely part of the effort. Yeah. Mm-hmm.
Finding the focusing with the path vector, I think you said you compare the distance between the two and that of the hits. The mesh circles?
For the vertex finding, yeah. Let me bring the slide up. So we're not using truth information at all. Let's say, obviously, we use it in training, the network, but then we don't use it. So I don't know if the question was on whether we are using truth information. No, we are using the hits, the input hits. before we start to aggregate them into clusters, et cetera, et cetera. And then for each hit, the network gives us a prediction, but it does so like it's fully trained, so we don't need to provide any truth information. Yeah, and then we create this heat map. I don't know if that answers the question.
What did we just listen? And which all the parameters for each of the regions?
Oh, for each of the circles. So the radius is given by what the network predicted in terms of how far the hit is from the vertex. So we draw, because the network gives us a prediction, but it doesn't tell us the vertex is down. It doesn't tell us which direction in, right? So it's a possible circle of a vertex position with respect to the hit you're considering. So that's why you have to then intersect all of these circles for the different hits. Yeah, I think with this the person who actually developed this, obviously knows a lot more about this. I think he's tried different kind of granularities as well. So I think aggregating hits as well. I think actually what we're doing now is a two-pass approach where there's a first coarser pass that isolates the region more broadly, and then we zoom into that region. And I think at that point is per hit. Yeah, I think that's how the latest is. Yeah. Yeah, sure.
So earlier on, like slide 11
Mhm.
or something, you said I was expecting to be able to run a fast order.
Yeah.
Years.
Yeah.
Years from
The beam turning on and having the first two far detector modules. So it's a goal for phase 1, for doing phase 1. Yeah. Mhm.
Stage about
Oh.
the gaps.
Yeah.
How do you anticipate those gaps arising? Would that be because eventually higher fails, or is this sometimes you just get gaps?
So some gaps are just gaps between, so they're just, built in the detector geometry. So they're there. And so in fact, this algorithm I'm talking about, it crosses, I think, registered detector gaps. It doesn't cross spontaneous, like a gap that is there, maybe because either something failed or because the projection was such that it just wasn't a hit that made it there. I don't know. So this kind of gap, this kind of algorithm would need to be aware of where the detector gaps are. But you can totally, then we have other algorithms that still try and walk a little bit farther ahead, even if there wasn't a detector gap, and try to bridge that other kind of gap as well. Yeah. But yeah, we provide a geometry description of the detector to our reconstruction. So the reconstruction is not agnostic to where the boundaries are, where the gaps are. And we do this in that interface I was talking about, where we provide the inputs. We also provide a geometry description.
More questions? If not, then let's thank Maria one more time.
Thank you. Thanks very much.
Maria is going back to Lawrence tonight, so if anybody wants to chat with her, she'll be around for
A couple of hours.
yeah, for a couple more hours before she gets her car back to Lawrence. So okay, thanks everybody.
Thank you very much.
We have our